Hi, welcome to Chapter 10. In Chapter 10, we're mostly going to be talking about heat and electricity. In this first chapter, we're going to talk about how heat is transferred from one substance to another. And this is a bit of a revision for you, so hopefully it's fairly familiar. So, the first thing we're going to talk about is conduction. There are three types of energy transfer that you should be aware of. First is conduction, second is convection, and the third is radiation. So the first we're going to talk about is conduction. So the way conduction works is it's basically the transfer of heat through a substance as a result of neighbouring vibrating particles. So let's imagine a solid here, and in a solid, as you know, we have all these different particles. And the particles are kind of just, wobbling on the spot. They're just kind of sitting there and they're wobbling back and forth. Alright, so they're relatively low energy, but they're very, very close together. So if we put a fire underneath them, or let's imagine a fire from the top somehow, the particles here would start to shake a bit more, and then that energy would cause the other ones to shake, and then that energy would pass through the substance. And as it passes through, these particles rather, as they shake more and more, they separate and they collide, and they slowly might turn from a solid to a liquid. And then as more and more energy goes in, the particles are now very far apart, and conduction isn't as easy. It's easier to warm a solid or a liquid than a gas by putting a fire underneath it. So that's conduction. So conduction again is the transfer of heat through a substance as a result of neighbouring vibrating particles. All right, so it's heat travelling through a substance that's kind of close and touching each other. The second one is convection. So convection, we see convection heaters, convection ovens, that create this cycle of rising and cooling. Okay, now as we know, hot air rises, so the hot air rises, it gets up to the top, and as it gets up to the top, it's farther away from the heater, and then it falls again, because it cools down and then falls. Alright, so imagine, cool air is down here, and there's a connection between convection and conduction that we don't often think about. As the cool air is down here, not only is it closer to the heater, but it's also closer to each other. Yeah. So because the particles are closer to each other, that means conduction can happen more easily. Because remember, we just said that when the particles are closer together, conduction can happen more easily. So as the heat comes in, the particles conduct the heat between themselves very well, but then they spread out, they get all energetic, and of course, because they're more energetic, they're going to fly up and around, and then because they're up and around and they're further away, that means that the energy can no longer pass easily between them, which means they cool down, which means they lose energy, which means they come closer together, which means they fall, which means that they're closer together, and then they can be heated up again. Alright, so that creates this cycle of hot and cold particles, hot and cold air normally, but it can also be water and various other things. So we have, what do we have so far? We have conduction, where the energy travels from particle to particle that's closer together. Convection, where the particles heat up and cool down as they move through an area. Let's have a look at the third. Third one is radiation. So radiation is what's called radiant, or it might be radiant heat. So radiation, unlike conduction and convection, doesn't really require particles to transfer the heat. It's just it's electromagnetic radiation, which is what we studied in the last chapter, if you remember. Okay, so with transmitted heat, for example, you can get heat kind of coming through glass and whatever else, but with radiated heat, it's less difficult. So there's three different types of radiant heat, I suppose. There's transmitted radiant heat, absorbed radiant heat, and reflected radiant heat. So some objects like glass, etc., allow radiant heat to go straight through them, and that's called transmitted Some objects are like a black, piece of, car fabric or something. I know the inside of my car gets very hot because we've got black seats. That'll absorb the heat. All right, and then there's the reflected radiated heat that reflects. I don't think there's anything too complicated there. Look at a very nice example of all three of these things. So let's look at this as two different situations here. This one's day and this one's night, but we'll look at day first. So during the day, radiant heat from the sun comes down and it warms up the earth. All right. Now, just due to the nature of the different materials, the land warms up faster than the sea does. All right, so we have very warm land and not so warm sea. So because we have very warm land, through conduction, the air that's close to the land warms up, and as the air close to the land warms up, the particles become more excited and they rise. Now, because the air has risen here, and also because it's more separated, all this cool air tends to come in from the sea, and that's why we get this cool sea breeze. Have you noticed that? Like, you can be standing next to the sea, there's almost a constant kind of cool breeze coming in from the sea. It's not, a normal large-scale weather effect that's causing that. It's this small scale or smaller scale conduction effect that's causing that. Alright, so we've got this cool air, cool breeze, cool sea breeze coming in here. The warm air is rising, and of course as the warm air rises, their particles separate. They can no longer conduct heat as well. And also they're rising to a higher altitude, which is further away from the warm land, or even the or in the sea, and then it cools down and it falls back down to the sea, and then fills that space again, and so you get this kind of conduction kind of effect going on here as well. I think kite surfers take advantage of this as well. Now, that's all very well and good during the day, but what happens at night? Well, at night it's kind of the opposite. The land becomes cooler than the sea does. All right, so although the land gets warmer during the day, it loses its warmth faster than the sea does. So all of a sudden the land is cooler and the sea is warmer. So, and there's no radiant heat. The moon doesn't cause radiant heat. There's no radiant heat. So what's happening here is that the conduction from the warmer sea is heating up this air. That's rising. The cool air is blowing out, all right, from the land to the sea. And then causing, this convection effect in here as well. So this neat little example, you can really talk about all three different types of, energy transfer: conduction, convection, and radiation. Now, what I want to talk about here is vacuum flasks. Vacuum flasks, or thermos, was invented by a British chemist. By chemist, I mean like someone who does chemistry, named British Dewar. Now, he invented something called the Dewar flask. And the Dewar flask is... Well, the trick to a Dewar flask is this little gap in here. That is a partial vacuum. So he sucks all the air out, so there's just a vacuum in here. Now, as you know... heat can't be moved from one space to another without particles. Through radiant heat it can, but the vacuum doesn't allow the transfer of particles. All right. Furthermore, he's got the silver facing surfaces. Alright, so the silver facing surfaces, as we know, with radiation, it tends to reflect heat. So all the radiation is being reflected, and all the, conduction can't occur, and any convection can't occur. Alright, so, what this means is that this Dewar flask, or thermos, can carry your hot soup for quite a long time. I don't know if anybody ever uses these, but they're really effective. You know, you can put some hot soup or hot coffee or whatever it is in there, and they'll stay hot for the entire day because, you know, the heat can't get out via radiation, and it can't get out via conduction or convection. All right. Another example, more tasty example, well, it depends on what you put in the thermos, I suppose, but this is what's called a bomb Alaska. So this is a scoop of ice cream surrounded by meringue. So the meringue absorbs the heat. What happens here is that, you know, if you put a blob of ice cream in the oven, the ice cream would obviously melt, all right? But in this case, what you do is you put the blob of ice cream surrounded by the meringue in the oven for up to 3 minutes. It's 230 degrees Celsius in there. So normally the meringue would melt, the ice cream would melt, but because it's surrounded by all of this meringue, all the meringue absorbs all the heat, okay? And you can see they've actually gone over this meringue with a blowtorch as well, all right? So none of the heat from the oven or the blowtorch can get through this meringue and melt the ice cream inside. Alright? Good. Okay, so what I would like you to do is I would like you to go to 10.1, put all the blue words into Quizlet, and answer some questions 1 to 8. Thanks. See you in class.